Hello, we're a team of 8th graders called Spinnovation. I'm Adam Edwards.
I'm Sean Buckley.
And I am Blake Clark.
And we are trying to change the way you think about wind turbine blades with a new, more efficient model. This is our wind turbine blade. It was created with popsicle sticks, aluminum foil, and duct tape. We initially designed the blade to be able to pull instead of being pushed, and we'll kind of explain those aerodynamics later. But because we used materials that were so cheap and, I don't know, how heavy and how easily they came out of shape, it really could not keep that aerodynamic structure that we wanted. This little diagram here shows what pushing is. Basically, the wind just hits the object, like the turbine blade, and this really is not efficient because it's not pulling or using any kind of aerodynamic structure, and it's fairly heavy and wide if you're going to create a push kind of blade, because you need to be able to capture that kind of wind. Pull kind of system where the blade splits the wind, where the wind is going slower on the bottom side and it's going faster on the top side, so it can reach the end at the same speed. And this creates a low pressure and high pressure system. And anyway, the push and pull system, right here, the blade is being pulled to the low pressure area, and this is much more efficient because less material has to be used to create the wind turbine blade. Okay, like already mentioned, this type of blade that we initially created was supposed to be a pull system, but because it is so flimsy, as you can see, and the materials used were not necessarily strong, it ended up being a push kind of blade because the wind would hit it, and instead of it being large enough on this side to actually split the wind, it is rotated enough to where it can be pushed. So this is the actual data we found for our experiment. If you go down, you can see our hypothesis. That's not important right now, though. So in our analysis, I actually want to show you the calculations we created. We found that our model produces 0.5 watts in 5 seconds at 10 miles per hour. We needed to calculate the total amount of energy produced in an hour at 30 miles per hour to compare in our design notebook. Here are our calculations. We first needed to calculate how many watts will be produced in an hour. So we divided the total wattage, 0.5, by 5, so we can have 0.1 watts per second. And then we multiplied that by 60 for an entire minute, and then 60 again for the entire hour. So we're producing 360 watts per hour at 10 miles per hour. Next, we need to convert this to 30 miles per hour. We're at 10 right now, so we multiply by 3. 360 watts times 3 is 10,080 or 1,080 watts. Okay, our model produces 1,080 watts in 1 hour at 30 miles per hour. But we are not done. We need to find the watts produced per square foot of blade. Our current blade specifications are so: 2 feet length and 0.2 feet width. The total area of our blade is 0.4 square feet. So we need to finish our calculations by dividing 1,080 by 0.4. So basically, 2,700 watts are created per square foot. Thank you for watching.